When solving dependent motion problems, consider first the most important factor, which is how many cables are in the system. So you can see in this left example, you only have one cable. It's only one lengthy cable that's connecting everything. And also in this system, you only have one cable. So if you have one cable, it means that you only have one equation for the length of the cable. And here are some examples of two cable systems. So on the left side, this is 1, 2, 1, 2, and also here cable 1 and cable 2. And note that if we have two cables, this means that we need two equations, one equation for each cable. In problems that include motors, you need to specify a coordinate for a point on the cable that is going to the motor. So for example, here we specify a point, we give it a name A, and then we put the coordinates for point A and for the other moving parts, which is point B and point C. And in a similar type of problems, like this one, for example, you need a relationship between the car C and the barrel B. So it doesn't matter here if you choose the point at this side or at the other side, as long as the point is on the same cable. And it's even better if you specify the barrel coordinate first, which is SB, and then specify from the same reference the point C and the coordinate SC. And if we consider this system, let's say that we need to find the velocity of the motor, which is point A, and the velocity of the block, which is B. In this case, we need to find the length of the two cables. So for the first cable, it is going to be SB plus SB minus SC multiplied by 2. For the second cable, it will be SC plus SA. And since SC is involved in both relations, we need to take the derivative of the first and second equations. So you can see that VC is still involved, but we don't need it, so we will eliminate it. So for example, we'll take it from the second velocity equation and put it into the first one. And by doing this, we get 3VB plus 2VA equals to 0. And the derivative also is the acceleration relationship. However, in this system, note that we have only one cable. This small part is fixed and it doesn't count. So for this cable, we have the following: 2SB plus this length, which is going to be SB minus SC. And if we take the derivative, we can find the velocity and acceleration relationships. And note that it doesn't matter how the problem looks like. So for example, you can see this problem, but in a different configuration, like this one. Notice the fixed ends, and this is our equation for the first problem. Now for the second problem, we'll do the same. Just specify a point going to the motor, specify the coordinates for the car, for example, C, and a coordinate for the point going to the motor, which is SM. And adding these together, we have 2SC plus the small segment, which is SC minus SM, and it leads to the same problem exactly. And even in situations like this one, where the problem looks complicated, but it is really not, just apply the rules. So you have only one cable, which means you only have one equation. Put a datum for the moving objects, for A and for B, and then calculate the length. So for the first part here, you have 2SA plus SB plus the last segment, which is SB minus SA. And don't worry about the location of SA here, because it is a particle, so you can place SA anywhere. Up or down, it doesn't matter. And by taking the derivative, you will find the velocity and the acceleration relationships.